Hi, welcome to this video number 3 on laminar flow analysis in ANSYS. And in my previous video, I was able to define material. We said it's a fluid. We said my water, and we defined density and viscosity so that we can get a Reynolds number of 100. Then we are able to define boundary conditions. We defined all of them. Inlet, if you go back to the properties, we say the inlet is 1 meter per second axially on the along axial axis. Radial is 0 and supersonic we are not defining because we are not on a high speed regime. And we defined the operating conditions, and we said we're going to use 1 atmosphere, that is 125 pascals, and we are not considering effects of gravity. Our model is ready to start iteration. One thing I like doing is if you go now to solution here, I want to see the monitors. I want to go to the monitor schedule. Now we now need to define another solution. Go to the monitors residual. Remember we said we need for the in laminar flow we conduct what we call momentum balance and mass balance, and we want to determine the mass balance residuals. This means the mass inlet, the difference between the mass inlet and the mass outlet. Maybe if I go to an element, the mass inlet here and mass outlet, that difference should be this value, because we are looking on continuity. This value we want to determine here. I want to use 0. This value maybe 1. Let me use 1 to power minus 6. This means the error we get here will be of 1 to e to power negative 6. This is the difference between the mass balances, the mass inlet and mass outlet. The differences should be this value. Therefore, I say, okay, I'm defining the error within which our solution should comply. Then I need now to initialize. I want to initialize our analysis. If you go to initialization here, we have two types of initialization, hybrid and standard. Let's use hybrid. I will explain later what is meant by hybrid. For the axial velocity, I want to use 1. I want to use the entry. I want to assume the initial value when t is not, t naught. These are the initial values. Initialize. Therefore, if you go to the monitors, we have defined this already. Yeah. Let's first for run fast iteration. You go to run calculation here, and time step be automatic. Leave everything as default for now. Let everything be default. Let's get one iteration, just one, and calculate. Okay, it is complete. Let me go back to the graphics. I want to see the contours. If you go to the results, contours of, I want to check of velocity along axial velocity. Let's display. Let's see what it is. As you can see here, at the midline, at the center line, we are getting 1.22, but at the wall, we are getting 0 velocity. Therefore, the parameter, the liquid along this wall has 0 velocity. If you want to check the node centers, let me just say display. I want to display the mesh, and then I want node values here. Display. You can see now the velocity. Now remember, these node values means the velocity at the nodes. But now when you unselect node values, you are checking the velocity at the cell center. Now you can see the velocity at this point is this value, but as you progress becomes 0. And the velocity at the center becomes 1.2. Let me show node values so that we can see the velocity at the wall is 0, but the center is 1.2. Let's run again here. Let's do 5 iterations. Calculate. Okay. It iterates 5 times. Now the velocity at the center becomes 1.74. Can see here. But if you check the residues, remember we defined that the solution should stop once this value of continuity. We define these residues as the mass imbalance. This is the mass influx and mass outflux. The differences should be within 1 to a or 0.6. As you can see, the mass imbalance is almost a straight line. Therefore, if I go back to the graphics, contours, let's check the mass imbalance. Residuals here, mass imbalance. You can only check mass imbalance. You can see now the mass imbalance, how it is to power 0.8. You can see you're getting a negative, and some scenarios you're getting a positive. Let's see the pressure display. You can see the pressure, how it is. But now our main interest is velocity. That is, if you see the magnitude, I want to see the axial velocity. It's the same thing because we assumed that it is an axis symmetric, meaning the velocity doesn't vary perpendicular to the screen. If I go back to the run calculation, let me iterate 1000 times now. Okay, and see the scale here. You can see the mass imbalance. If you go back to the scaled, okay, I want to see here. You can see this one here dropped until it reached 1 to -6. Can see this point here. If you go straight, this mass imbalance, once it reaches here, it stops iterations. And you can see, I said iterate 1000 iterations, but it is stopped at around 58. You can see these are the iterations. It only performed 60 iterations. It did not perform 1000. But if you change this value to maybe to 8 to power 9, it will continue iterating until the mass imbalance, this one here, monitors residual, the value defined here is achieved. You can see this value, it is this value here. The reason why our analysis had stopped. Therefore, if you go back to the graphics, I want to see the contours of velocity display. Let's see. You can see how it looks like. this we are getting 1.98 at the center, at this point here. Then we are getting almost 0 here. Once we draw the streamlines, you'll see this one will be like a parabolic. It will take the shape of a parabolic. Okay, let's now do more analysis of these of our parameters. Let's now do a little bit deeper. Okay, now to measure the convergence, as you can see, we are using residuals here. We are using this one here, this value, to measure the convergence of our solution. There's something else we can use to check. We can either use residuals and we can use drag coefficient. Let me explain what is drag coefficient. Drag coefficient monitor. Fluent finds the net force acting on the pipe wall by integrating the pressure and shear forces on the surface. If this is your surface, this is your wall, as the liquid is moving on this wall, we have two forces acting on the wall. The first force is called pressure force, that is perpendicular to the wall. This one is a pressure force, perpendicular to the wall. We have another force that is called shear force, that is, this one is a shear, parallel to the wall. If you integrate these pressures, you get overall drag onto this direction. You get drag. This one is called drag. And drag is newtons on this direction. This one is the shear. This one is the pressure force. This one is a shear force and a pressure force. As you can see, the shear force contributes to the drag on this direction. If you monitor the coefficient of this drag, you can now determine the convergence of our solution. Drag is a component of this force vector in the axial direction. The component of this vector in this direction is the drag. Drag coefficient in our case becomes drag. You divide by the dynamic pressure. This value is dynamic pressure, and you're using average velocity multiplied by weighted area. This is the area of our surface that is in contact with the liquid. Remember, if you take dynamic pressure multiplied by the area, you get force in newtons. Therefore, if you take drag in newtons divided by this value in newtons, you get a coefficient that does not has dimensions. This one is dimensionless. Now in Fluent, we're going to use reference pressure, ref, defined here. We're going to define that, not pressure, density. We're going to define that value here. At the reference values here, we're going to define density. We're going to define density. Then we're going to define this value, reference area. Then we're going to define all these other parameters, velocity, so that we can get drag coefficient. Just note this, drag coefficient acts in axial direction. It is a component axially of the shear force. Therefore, if you integrate these two forces, pressure and shear forces, you get drag. And the Fluent can do that for us. Let's now implement this concept in Fluent and see what happens. Let me now show you how you can monitor the drag coefficient alongside alongside the residues as the iterations proceed, so that we can keep or track iterative convergence for the linearization error. Therefore, for me now to to monitor the drag coefficient here, I need to go to the report. If you go to the report definition, uh, if you double click report definition, because we want drag coefficient to be reported back to us, you can select new. This later I will show you how you can also report this, but today we focus on the drag. We can report drag, lift, moment, and force, but for now let's do the drag. Name to be CND, that is a drag coefficient. Report output type. We just need coefficient. We don't need a drag force. In case you need a drag force, you can check here. And we want to report on the pipe wall. Then we need the vector, is the vector along that is axial, not radial. This one is axial. Remember, you're using an axis axisymmetric analysis. Along y-axis, we don't want the force along the y-axis, because we said the force, this force here, we don't need this one. We don't want the effect of this force. We only need the effect of the force for the that comes from the shear forces along this axis, this direction. Therefore, I want also to print the parameters on the console. I want to create a report file and a plot. If you say OK, close, then we need the reference values. If you use this formula, 2 pi RL, you get an area of 1.885. 1.885. This is the area you need to define. We said it is a weighted area, the area in contact, the area in which the liquid is in contact with the surface. Density of the liquid is 1, and length is 3 meters. Then if you go back to the initialization, I want to initialize again. Then I want to run calculation here. Before I do run calculation, remember we need to define, we have defined monitors. If you go here, residuals here, these values, they remain the same. Okay, these values remain the same. Make sure they remain the same under the monitors here. Let's now run calculation, browser iterations, calculate. Let's see the CD. You can see the coefficient drag. You can see now the value. This one has converged. You can see this one is almost straight. It means even if you continue iterating, this one will never change. As you can see, the value is 1.7 all through 1. This value is constant. Therefore, the drag coefficient is very good when you want to iterate to convergence very fast. If you want to see the files, if you go to the monitors, report files here, you can see the CD file. You can open the .txt file for the CD, and we can plot these files in Excel and see what happens. Okay, that's how you implement coefficient of drag. In my next and my last video for this program specification, we're going now to go deeper to post process where we create contours, streamlines. Let's go to the post process to dig deeper a little bit. Thank you. Stay tuned.